and then talk about some occupationally relevant agents that were recommended for evaluation by a recent advisory group. So IARC is an organization that both conducts research and evaluates evidence. The IARC monographs have been around for 50 years. We're finishing our 50th year just this year. We're known as the WHO's Encyclopedia of Carcinogens, and we've evaluated more than 1,030 agents now at this point. So the global cancer burden is very high and it's increasing. This is due to what we call the epidemiologic transition, changing demographics around the world, and also a shift of carcinogenic exposures to low and middle income countries. And we know that we can't treat our way out of this problem. Prevention is the single most effective response. The first step in prevention is to identify what causes cancer. And that's the subject of the IARC monographs. We also have a handbooks program that identifies what factors prevent cancer. So the monographs have had a dual role over the years in evaluating the evidence from latest scientific research and also stimulating new research to fill identified gaps. As an example, in 1997 to 2006, you can see here, there were only about 150 studies published on the topic of shift work. And this really exploded by about a factor of 8 after about 2008. And what was that due to? Well, we would contend that the publication of the first IARC monograph on shift work had a lot to do with this explosion of interest in the topic. So now moving on to our preamble, this slide just illustrates that we go from scientific publications in the literature to these several hundred-page iconic monographs, and you may wonder how that occurs. Well, it's all described in the preamble to the IARC monographs, which was first published in the very first volume. This gives all of the procedures that describe how the monographs are carried out. And it was been periodically updated by advisory groups about 8 times in the last 50 years. The most recent update of the preamble occurred 3 years ago in 2018. And you see here a picture of the advisory group. What had happened since 2006 that required a new update? Well, first of all, there had been many procedural advances in systematic review methodology, but also scientific advances in cancer epidemiology and carcinogen mechanisms. The IARC monographs evaluations are carried out in a 5-step systematic review process. In step 1, we identify the relevant studies. In step 2, we screen, select, and organize the studies. And these 2 steps are done by the IARC Secretariat. We are scientists in consultation with the working group. Steps 3 through 5 are carried out by the working group. They evaluate study quality in step 3. They report study characteristics in step 4. And in step 5, at an 8-day meeting here in Lyon, France, the evidence is synthesized, leading to an overall evaluation. The procedures for carrying out the monographs are described in the preamble, as I mentioned earlier, and it lays out the steps for participant selection, managing conflicts of interest, for conducting the meeting, and for the evaluation itself. The recently updated preamble emphasizes increased transparency and rigor in the systematic review, and it also modernizes the methods used to identify and tag the literature. So there's a link here to our amended preamble, which was published in January 2019. The monographs evaluations are done by the working group, which is independent scientists who are free from conflicts of interest. They're assisted by the Secretariat, who are scientists in our own right, and we help coordinate all aspects of evaluation, and we ensure guidance and ensure adherence to the preamble. We also have 3 groups of attendees who can attend the meeting but don't draft text related to the evaluation or contribute to the evaluation in any way. We are truly a global endeavor. Since 1971, there have been more than 1,200 scientists from over 50 countries who've participated in monographs meetings. The evidence that's considered includes cancer in humans, cancer in experimental animals, and mechanistic evidence. And exposure in humans is also a critical line of evidence, especially the exposure assessment quality. So we're going to take a closer look now at some of the steps involved as outlined in the new preamble. We use several software tools in our systematic review. There's something called the Health Assessment Workspace Collaborative, or HAWC, It's used to search, organize, and tag every study for inclusion or exclusion using pre-specified criteria. We conduct data extraction using pre-specified, data extractions conducted by at least 2 people per study and verified. The study characteristics are summarized in a standardized format, including strengths, limitations, and exposure quality considerations using a standardized piece of software. And these tools are described in a recent paper by some of our colleagues. So looking again at step 5 in more detail, each line of evidence, cancer in humans, cancer in experimental animals, and mechanistic evidence, is reviewed and synthesized by the working group. The categories for cancer in humans and animals are the same, but of course the evaluation criteria are quite different. So at the meeting then, the 3 streams of evidence are brought together to reach an overall evaluation of group 1, which is carcinogenic to humans with 121 agents now. Group 2A, probably carcinogenic to humans with 89 agents. Group 2B, possibly carcinogenic to humans with 319 agents. And group 3, not classifiable as to its carcinogenicity to humans with 500 agents. So let's look a little more closely at how the evidence is evaluated. And I know you're all interested in epidemiology, so that is our cancer in humans section. To reach a determination of sufficient evidence, the working group concludes that a causal relationship has been established. And in that we mean a positive association is seen in the body of evidence, and chance, bias, and confounding could be ruled out with reasonable confidence. For a determination of limited evidence, the working group concludes that a causal interpretation is credible. However, chance, bias, and confounding could not be ruled out with reasonable confidence. For an inadequate determination, the studies permitted no conclusion about a causal association, or very commonly, no data were available. The 4th category, ESLC, stands for evidence suggesting lack of carcinogenicity. And for this determination, high quality studies covering the full range of exposure are all consistent in not showing a positive association at any level of exposure. And this is an uncommon designation to reach, but it is sometimes used when, for example, there's an inverse association between an exposure and a particular cancer type. And an example could be coffee consumption and endometrial cancer. Now, how does the working group carry this out? Well, they consider the quality and the informativeness of the cancer epidemiology studies, the quality of the exposure and cancer outcome assessment, the potential for selection bias, whether there was adequate consideration of confounding, the quality of the data collection methods, and the appropriateness of the statistical analysis methods. In addition, they consider the informativeness of the study. In addition to quality, that is, does the study have the ability to detect the presence of a true association or the absence of a null association? This goes beyond study power to consider things like exposure contrast, latency, and exposure to the target organ. So there are a bunch of methods used to ensure consistency and transparency. The critiques are drafted by experts not involved in the study. There are cross-subgroup discussions on important issues related to things like exposure assessment quality, and there's comprehensive peer review, first among the cancer epidemiology subgroup and then across the whole working group. In addition, we've really started to emphasize the evaluation of impacts of biases because every observational study has the potential for bias. First, there's an explicit consideration of exposure assessment quality and their anticipated impact on measures of association. Working groups commonly use triangulation of evidence. For example, there may be case control studies that have one source of bias, like recall bias, or cohort studies that have another source of bias. And if different studies with different potentials for bias all point in the same direction, that can be strong evidence in favor of a causal association. Working groups have used causal diagrams to better elucidate confounders. There's no need to adjust for factors that are non-confounders, and in fact, you may create confounding where none existed. Using study designs that could be more informative for certain exposure types can also be powerful. For example, Mendelian randomization can be a powerful way of controlling for confounding. However, this is uncommon for occupational exposures because These exposures don't have a strong genetic component. The use of negative control outcomes is commonly undertaken. These are outcomes plausibly related to confounders, but not to the agent of interest. And I should say this approach is often used in cohort studies because of the ability to look at multiple outcomes at the same time. Now, when you have information on a confounder available for no subjects or only for some subjects, you can evaluate indirect adjustments for confounding. And we did this in the beryllium study because we had partial smoking information for the cohort. You can also use a theoretical adjustment based on worst case assumptions about the confounder exposure distribution, which is useful when you have no data about confounding. In synthesizing the human cancer evidence, the working group uses an adaptation of the Bradford Hill viewpoints. Strengths of association can be very important, but remember that weak associations that have high public health impact may in fact be causal. The consistency of the association is important, but this needs to be tempered by the study's quality and informativeness. So not all studies are weighted equally. The presence of an exposure response, as I mentioned, can be a powerful indicator of causality. Temporality is a critical factor, and just as an example, we just published yesterday a monograph on opium consumption, and there the temporality, the potential for reverse causation was a key consideration. Lastly, biological plausibility is sometimes an important consideration. So another new feature is that there's a detailed evidence synthesis section, which incorporates assessment of impacts of chance, bias, and confounding on the causal conclusions, and it includes evaluations specific to each cancer site that has evidence. It gives explicit documentation of the working group's rationale in reaching a conclusion. I won't spend as much time on these other streams. This is the cancer in experimental animals, except to note that there are predefined criteria for evaluating each of these 4 categories. The mechanistic data is probably the evidence stream that's changed the most in our new preamble. And this was arrived at because of challenges in systematically searching for relevant mechanisms, bringing uniformity across the assessments rather than having working group members always highlighting their favored mechanism. In addition, there's been a real explosion in mechanistic evidence over the decades and concerns about how to efficiently evaluate these databases. So in volume 100 of the IARC monographs, which was a reevaluation of all the group 1 agents, workshops were put together to try to see if commonalities could be identified in mechanisms across these known human carcinogens. And this workshop came to the conclusion that they could identify 10 key characteristics of carcinogens. These are chemical and biological properties of the established human carcinogens. Data on key characteristics can provide evidence of carcinogenicity even in the absence of bioassay or cancer epidemiology evidence. And they can be used to assemble data relevant to mechanisms without having the need for an a priori hypothesis of the mechanism. So in our searches, we have identified search terms that can be used to identify studies pertinent to each of these 10 characteristics, which are described here. And some of them would be familiar to you who know mechanistic evidence, like genotoxicity, altering DNA repair or causing genomic instability, inducing oxidative stress or chronic inflammation are common mechanisms of carcinogenicity. The viruses are known to be immunosuppressive, along with some other interesting exposures like welding fumes. Modulating receptor-mediated effects. Agents like dioxin have this as their main mechanism. And agents like use of hormonal birth control or menopausal supplements also have this mechanism. So you get the idea. And these 10 key characteristics are all subject to change depending on the evolution of mechanistic evidence over time. So here's an interesting graphic showing the key characteristics all aligned. And in the slides, you'll see some relevant references that you can refer back to for more information. So how are these brought together to evaluate mechanistic evidence? Well, there are 3 different determinations that could be made: strong, limited, and inadequate. For a strong call, results are seen in different systems and they're consistent. The overall database is coherent, and the studies cover a range of relevant endpoints in different mammalian species, hopefully including humans. For a limited call, the data are suggestive, but for example, the studies may cover a narrow range of experiments or endpoints or species, or there's unexplained incoherence across well-conducted studies of different designs or different endpoints. Inadequate call is based on data that's just generally less available or of high quality. So how then do these, there's an additional wrinkle for the mechanistic evidence in the sense that there are three distinct topics that influence these evaluations. One of them is the so-called mechanistic class. This is a determination that an agent belongs based on mechanistic considerations to a class of agents, one or more of which is probably carcinogenic or carcinogenic to humans. And an example of this is, we recently had an evaluation of a bunch of aromatic amines. And these are used in dyes to produce dyes. And a number of them, like aniline, which is a very common dye in the industrial setting and used in producing lots of building foams, for example. The evidence that was seen in the mechanistic data looked a lot like another group 1 agent called orthotoluidine, which is a similar aromatic amine. And so the working group decided that aniline belonged to a mechanistic class of aromatic amines. And so that is a strong evidence determination. A second line of evidence could be the key characteristics of carcinogens. And these could be in exposed humans, in human primary cells or tissues, or in experimental systems. A third determination could be that a mechanism that operates in experimental animals is not relevant to humans. So usually this last criterion is not invoked when you have strong mechanistic class or strong key characteristics of carcinogens. So I think I'll skip over this slide in the interest of time, but note that studies in humans are subject to all the same considerations that we would use for studies of cancer in humans. But again, then you have to consider the endpoint as well. So then how are these three streams brought together? Well, first of all, there's a single step integration for all three streams of evidence. There are 4 possible classifications, which I've already presented to you. And a distinction was made between group 2B and group 2A. Group 2B is based on a single stream of evidence, and it's less than sufficient in humans. Group 2A, on the other hand, is based on 2 streams of evidence, at least one of which is in humans, and it's less than sufficient, or human cells. So those are how we distinguish groups 2B and 2A. For group 1, sufficient evidence of cancer in humans is always grounds for a group 1 evaluation. However, if you don't have that, but you have sufficient evidence in experimental animals for cancer and strong mechanistic evidence in exposed humans, a group 1 classification can also be reached. Let's look now at some recent evaluations following the preamble update. So we had a sufficient call for opium consumption with sufficient evidence for cancers of larynx, lung, and bladder, and limited evidence for cancers of pharynx, esophagus, stomach, and pancreas. We evaluated night shift work back in 2019, and I see that Ryan Diver is in your audience, and he was here for that evaluation. It was very exciting. We found limited evidence for cancers of breast, prostate, colon, and rectum. I'm sorry, let me go back one slide. So in addition to limited evidence for humans, we also had sufficient evidence of bioassays in experimental animals and strong mechanistic evidence. So that combination of limited and strong mechanistic or limited in cancer bioassays, each of those would get us to group 2A. We didn't have strong evidence in exposed humans, but if we had, it would have reached group 1. We evaluated acrolein about a year ago in volume 128, and here we had a group 2A determination with sufficient evidence of cancer bioassays in animals and strong evidence in human cells or tissues, but not exposed humans. And then we had several aromatic amines, as I mentioned, aniline, ortho, and nitidine, and an epoxide, glycidyl methacrylate, that were for which a strong mechanistic class argument was invoked, and they reached 2A. We also had a number that were 2B on the basis of sufficient bioassay evidence. Some of these had strong mechanistic evidence as well, but some had just sufficient bioassay evidence. And then we had at least one agent that was in group 3, which did not reach sufficient or strong in any evidence stream. So I'll close now. I realize I'm getting near the end with just to touch on what's coming up in the monographs. So every 5 years, we convene an advisory group to review the evidence of what might be a useful or an informative agent to evaluate. And at this meeting, which was held in the spring of 2019, we had an advisory group that evaluated about 170 agents that were nominated by the public or public health agencies or scientists. And this advisory group rated 120 out of the 170 or so as being high, medium, or low priority for evaluation during 2020 to 2024. And this is a rather dry presentation of them. So we created this more colorful poster, which I have printed and sitting above my office, and I look at it every day. But here they're grouped by type of agent, and also the colorful, the colors are codes for the types of evidence that contribute to the nomination. So we'll take a closer look at these, but just bear in mind that red means mechanistic evidence alone, blue means human cancer evidence alone, yellow means cancer bioassay evidence alone, and then the combinations of these primary colors indicate combinations of evidence. So looking at human cancer, we have green if it's combined with bioassay, purple if it's combined with mechanistic evidence, and this bright multicolored color indicates all 3 streams of evidence. Lastly, the agents that are inside the inner circle on that graph are given high priority versus the ones on the outside, which are medium or low. So let's look at the ones that are occupationally relevant. Up in the upper left quadrant, we have a lot of dyes, solvents, and other chemicals. And you can see here that the colors tend to be red and orange and yellow. And this means there's really no human cancer evidence for these agents. So it's kind of interesting that it panned out in this way. 2 exceptions are nitrotoluene, which was low priority, and tetrachloroethylene, or PERC, for which we have a lot of evidence from studies of dry cleaning workers. A meeting that's coming up in a couple weeks' time includes 1,1,1-trichloroethane, and we're very grateful to have Michelle Turner as a participant at that meeting, as well as a number of other agents in this quadrant. Down in the lower left-hand quadrant, we have complex exposures, which does include a lot of occupationally relevant agents. Interestingly, automotive gasoline had evidence from all 3 streams. Sedentary behavior, including sedentary work, was accorded high priority, largely on the basis of human evidence, human cancer evidence. Firefighting exposure, which we're evaluating next summer in June, has human cancer and mechanistic evidence, as does semiconductor manufacturing. Up in the upper right quadrant, we have flame retardants here on the left, and pesticides. And the flame retardants, which include some perfluorinated compounds, pentabromodiphenyl ethers, PDBEs, bromate compounds, parabens, they tend to have mechanistic evidence and bioassay evidence, but not a lot of human cancer evidence contributing. Although this does seem to be evolving for one perfluorinated compound in particular, PFOA, which has had an increase in number of studies available since this meeting was held. The pesticides, by contrast, you see a lot of purple, a lot of multicolor. So this means there's a mixture of human cancer and mechanistic evidence, or all 3 streams of evidence. And then further down this graph, we see the metals, particles, fibers, and radio frequency, electromagnetic field radiation. And these agents do tend to have human cancer evidence. Some of them have bioassay. Most of them do have mechanistic evidence. We're looking at cobalt and antimony trioxide and weapons grade tungsten, which is here. So these are coming up in the spring of this year. So after 50 years, in summary, I can say that the identification of human carcinogens remains as important as ever, given the high and increasing burden of occupational and other cancers. I think the monographs are well positioned to retain and extend our role as the WHO's encyclopedia of human carcinogens. The modernized preamble has increased the robustness and transparency of the evaluations. And we have a lot of priorities on our list that include occupational data and occupational cohort data for just about all the studies that have human evidence that I showed on that previous set of slides. Occupational cohort studies are right in there in providing evidence in support of the carcinogenicity evaluation. With that, I'll acknowledge all of my colleagues in the monographs program, past and present, and our funders. We just were awarded our 41st to 45th year of funding from the NCI for this program. So we're really grateful for all of the investment that the US research community has given to the program over the years. And with that, that is everything. I'm happy to answer any questions that you may have on either of these. I don't know what the next part of this would be, Michelle.